So in this video we will study the concept of countability in sets. So let's define the definition of countable sets. So countable sets, so any set which is finite or it has the same cardinality as the set of positive integers. So any set which is finite, obviously which is countable. So and if a set has the same cardinality as the set of positive integers, it is said to be countable. Okay. What is the immediate result of that? What is the main property of the set of positive integers? The main property of set of positive integers is that it can be listed. So for example, if a child is starting to learn numbers, typically he starts from 1, 2, 3, he starts counting them, right? So positive integers is intuitively and naturally related to counting. So if any set is countable, then this means that we can list its items. And by listing, what I mean is, for example, we have a set A maybe, which is A1, A2, A3 and so on. Now if this is countable set, then we can say that this is f of 1, this is f of 2 and so on, where this f is any function, any one-to-one correspondence, right? So any set which can be listed is a countable set. By definition, any set which has finite number of elements and it has the same cardinality as the set of positive integers is a countable set. Okay. Now we come to the difficult part. Now what we are going to show is that set of rational numbers is countable. Okay. Now this seems counterintuitive because we have so many rational numbers and all of them are fractions, but we will see that we can actually list them. Okay, now let's start listing them. Now by listing, what I mean is that when we list them, then we won't skip any intermediate rational number when we list two rational numbers. Okay, now by definition, what is a rational number? Rational number is a 1 which can be written as so for example, if A is rational number, so it can be written as P over Q, where P and Q are integers. Okay, now let us have some rule to list them. So here we will say P plus Q is equal to 2, and we will say P plus Q is equal to 3 and so on. So now I'm going to list all the rational numbers for which, and I'm thinking of only positive rational numbers right now. So all rational numbers for which P plus Q is equal to 2. So there is only one rational number like that, which is 1 over 1. Then all the rational numbers in which the sum is 3, so I have 2 of them. Then all the rational numbers in which the sum is equal to 4, which is I have 3 of them. But this 2 over 2 is already taken care of here, so I'm going to cancel. So 2 over 2 is 1 and 1 over 1 is already taking care of that. So next one, when P plus Q is equal to 5, so I will say 1 over 4, 2 over 3, 3 over 2 and 4 over 1. Any repetition here? I don't think so. Okay, then we come to 6. So 1 over 5, 2 over 4, 3/3, 4/2, 5/1. Now we have many repetitions. So 2/4 is already taken care of by 1/2, so we cancel it out. 3/3 is already taken care of by 2/2 and 1/1, so it's already done. 4/2 is 2, so that is also taken care of by 2/1. So this way we can list them all. So now note that since the set of rational numbers, since the elements of the set of rational numbers can be listed without skipping, we conclude that set of rational number is usually denoted by q. Q is countable. Okay, so this is it. This is the proof which says, which proves the countability of the rational numbers. And typically in discrete math, we tend to prove things which is obvious to us, but in the notion of discrete math, nothing is obvious, so we have to prove everything. Even if somebody asks us that set of integers is a subset of set of real numbers, it's obvious, but then we have to denote the set of integers in some way, and then denote the set of real numbers in some other way, and then do some set operations to prove that set of integers is actually a subset of set of real numbers. So this is one way to prove the countability of rational numbers. And there is another proof in which we can prove that set of real numbers is actually not countable, but that is a different kind of proof. Okay, so this is it for the countability and set of rational numbers. Hope you like the video. Thanks for watching.